Okay, let's do this electric field from a line segment, and we'll take the limit as L goes to infinity here, and we'll make this electric field from an entire infinite line of charge. So I've got a total charge Q here smeared out on the y-axis from negative L over 2 to L over 2. So the total length is L. We're going to calculate the electric field at a point X along the x-axis. Again, it's the symmetry that helps us do this. Finding the electric field at, say, some arbitrary point in space would be incredibly difficult. This one we could do, and it's a little harder than the last one we did, but not too bad. So we're always going to do these either with differentials, if you want to do it like that, or with Riemann sums. So I'm going to pick out a little slice of y here, call it delta y, up at some y position, called it yi here. The amount of charge that lives in that little slice, delta q, is the charge density, charge per unit length, times the length of that, delta y. Charge density is always total charge divided by total length. So my total length is L, so my charge density is Q over L. So the amount of charge that lives in this little slice, delta Q, I'm calling it, is Q over L delta Y. Charge per unit length times length. Then Coulomb's law says we pretend here, remember we're going to do a limit, we pretend that all of that charge is concentrated at a single point. Coulomb's law says the electric field caused by a point charge is K amount of charge over distance squared. So the electric field in magnitude is approximately K delta Q over R squared. R squared here, we use Pythagorean. This side is X, this side is Y. This side is R. R will be square root of X squared plus Y squared. So R squared is X squared plus Y squared. So that's the electric field. That's a vector that will point down this direction. Points down like this. And it has this magnitude, approximately. So just like last time with the ring of charge, all the EY's will cancel out here. So this little slice of charge is giving us a vector that points down. My EY is here, my EX is here. A corresponding portion of charge down here would give us a vector that points up. Those two EY's would cancel, the two EX's would combine together. So adding up all the EY's will get 0. Remember, if you're ever integrating, we're going to turn this into an integral. You can never integrate over all the E's. You can't integrate these guys. You can add up all the EX's and all the EY's. You have to do this component-wise. EX here, just literally like last time, this is our angle theta here. Cosine of theta would be EX over magnitude of E. So EX is the magnitude of the vector times cosine of theta. But we can write that a different way in this problem. Not always. You're going to have a problem in the group quiz where you'll be integrating over theta. So you're going to leave thetas in the problem. Your variable of integration will be theta. But here, theta, or cosine of theta, using this big triangle, will be x over r. Then, EXI will be EX times cosine of theta. We throw in everything we found so far. Remember, delta Q was Q over L delta Y. KQ over R was E. X over R was cosine of theta. That's where all of this came from. Then the total EX will be adding up all of those little components. These were all approximately. This is still approximately. We take the limit as delta Y goes to 0, and that approximately becomes an equal. That sum, which is the Greek letter S, becomes a stretched out S, the integral symbol. that delta y in the limit becomes a differential, a dy. And then we put in our limits of integration. Y, that's our variable of integration, went from negative L over 2 to L over 2. So now we have to integrate this function. This is a function of y. Y is our variable of integration. Kx, q, and L are all constants. They don't depend on y. They can come outside the integral. Now we have to do this integral. And we could do it. You guys have all taken Calc 2. You could do this integral. It's a trig sub. Or we could just look this up in an integral table. So we're going to use this, the antiderivative of du over a squared plus u squared to the 3/2 is u over a squared root a squared plus u squared. So compare these two. In this case, y is playing the role of u, and a is playing the role of x. So we'll just plug everything in. We have our answer. We'll get y, where all the u's were, x, where all the a's were. Evaluated from, this was a definite integral, negative L over 2 to L over 2. Okay, and then check these details yourself. But in the bottom, I get a squared. To L over 2 squared, negative L over 2 squared, we get the same thing. So we end up with like terms. On the top, I'm going to get L over 2 minus a negative, or plus, an L over 2. So that's just an L. So once we throw in our limits and add them together, they are like terms, we get this expression. These L's cancel. One of these X's cancel, leaving one on the bottom. We get this expression. So this is the electric field from a finite line of charge a distance x away from the center of it. Let's take the limit as L goes to infinity and see what happens. So we want L much, much bigger than x. This is also the same thing as if x gets really small. So if we get really close to that line segment of charge, an equivalent formulation. But we'll think here in terms of Calc 1, taking a limit as L goes to infinity. Okay, so we got to be careful. If L goes to infinity, our total charge would also go to infinity. We want a constant charge density here. So we could either let Q go to 0, our total charge, or our charge density go to 0, and keep the same total charge, or we could keep a constant charge density, and that's what we're going to do. We want to keep lambda constant. So remember, lambda was Q over L, so Q will be lambda times L. Okay, so I just threw that in here. Now, we've got L's on top and bottom. We need to figure out a way to cancel those L's in order to take the limit. Otherwise, we get infinity over infinity. So same game we played last time. We're going to factor this L out here. So I'm going to pull an L out, keep it under the radical. Remember, this was all raised to the, here was our final answer. This is square root of the whole thing. So I'm going to pull that L squared out from this expression under the radical by dividing both of these by L squared. So I get an X over L squared, and then I pull this L squared out. So under the radical I have L squared, and then in parentheses, X over L squared plus 1/2 squared. Square root of L squared is just L. So I took the square root of this L squared. That L and this L will cancel. Now the only L that's left over is in this radical down here, and it's on the bottom. X over L goes to 0 as L goes to infinity. So I get 0 plus, it's hard to see, but there's a plus in there. 1/2, that's a 1/2 squared. Well, that's just square root of a half square. That's just a half. So do a little keep change flip there. That 2 pops up on top, and we get this expression. So the electric field from an infinite line of charge of constant charge density looks like this. So this is constant charge density lambda. So this is the expression we'll use if we want to find the electric field from a wire of charge. And if we're close enough to it, it may not actually be infinite, but it's close enough because we're really close to it. If it's a pretty long line and we're really close to it, we can pretend it's almost infinite. And the electric field will drop off like 1 over distance and will point directly away. So we're at this point. The electric field from a line of charge points away and it drops off like 1 over distance. So the electric field out here, if I go twice as far, would be half the field. And over here on this side, the electric field. So if I draw electric field lines from a line of charge, they'll all point away. And the further away we get, the smaller they'll be, dropping off like 1 over distance.